Today we're going to continue talking about refraction, and we're going to talk about something called the critical angle. In order to do that, we're going to do a few little warm-up problems so you can kind of get the idea of why there is such thing as a critical angle. So if you would turn your attention down here on the left side of the screen, we're looking at a ray of light that is coming out of the water into the air. Okay, so if you recall, water has an index of refraction of 1.333, and air has an index of refraction of just over 1. When we do calculations, in general, we're just going to use 1.0 for the index of refraction of air. We don't need to use as many decimal places as it actually has, like above 1. Okay, so when we look at this incident ray that's coming up from the water, how is it going to turn when it comes out of the water? Is it going to keep going in a straight line? Is it going to turn closer to the normal, or is it going to turn further away from the normal? That's the question. What direction is it going to go in? So in order to answer that question, let's go back to our example of the car or the truck coming out of grass this time onto the road. So here's your car. It's going to hit the road like this, so let's redraw it. Here are the tires. Yeah, they're not awesome. Okay. Which tires are going to hit the road first? Well, this tire is going to hit the road first. So whereas these tires on the right are actually still in the grass, they're actually going slowly. Whereas this tire right here, as soon as it hits the road, it's going to get good traction and it's going to want to speed up. So it's going to want to speed up. So it's going to cause the car to rotate a little bit. And instead of continuing in this straight line, it's actually turn and go like that. Okay? So we can say the same thing's going to happen over here with our incident ray. Instead of going in this straight line like that, it's actually going to turn and go to the right, a little further away. So if our angle 1 is small, our angle 2 here is going to be larger. Okay? We can actually see that this happened with the formula. We started with water of 1.333 and a certain small angle. Okay? Now let's see what happens when they go into the air. Well, the index of refraction has gone down. It's gone from 1.333 to just 1, so it's gone down. So in order to maintain this equation, what's going to have to happen to this angle right here? It's going to have to go up in order to maintain the equality on both sides. Okay, so if your index of refraction goes down, then your angle has to go up. That's one way to think about it. The other way to think about it is the truck example. All right, let's do a few examples with numbers. Here we've got some numbers ready to plug in. Again, in all 4 of these examples, we're going from water into air. And let's calculate the new angle that the incident ray is going to travel once it actually reaches the air. Is it going to turn, and what angle is it going to turn at? Okay. Before we try and solve for that second angle, you cannot solve this equation, Snell's law. You cannot solve that equation in your calculator, because if you solve for theta 2, which is actually what we're looking for, if you solve for theta 2 in your calculator, it turns out that sine, if we were to graph out sine, it actually repeats itself over and over and over and over again. So if you ask your calculator, where does sine equal a certain thing, you're actually going to get a bunch of answers. All of these would be answers. So your calculator doesn't know what to tell you, except that there's an infinite number of answers. So instead of asking your calculator to solve for sine of an angle, we're going to have to do a little bit of, we're not going to do that. We're going to have to do a little bit of algebra to begin with. And we can do it on the front end, and you guys can just remember it, or you can work it out each time. Either way you want to do it. Okay? So let's get theta 2 all by itself. Let's start by dividing by n2, put it on the bottom on the left side. So now we have n1 times the sine theta 1 divided by n2. And that's equal to sine theta. So how do we get rid of this sign? Well, we have to take the inverse sign, the arc sign of both sides. In your calculator, that looks like sine -1. And it's called arc sine, but they write it as sine -1 because it's the inverse function. It's the opposite function. So we've solved this equation now for theta 2. And this side right here, you can just plug right into your calculator. Okay, so let's plug in those numbers for the very first one, the 40 degrees. So we would get, if we were to plug in the same thing, sine -1. N1 is whatever our first medium is, which is water, so we'll use 1.333, times the sine of 40 degrees. And that's all divided by the second index of refraction. In this case, it is water. Okay, so in this case, it's just 1. If we do that in our calculator, we get 59 degrees. Let's come up here and label that 59 degrees. So it is turned a little further away, and it's now at 59. That's actually not a very accurate drawing of 59 degrees. Neither is that. Let's try one more time. I like it. It's just opened up a little bit. 59 degrees. Over here, we got theta 2 equals 59 degrees. Okay. So let's repeat this for 45 degrees. If you do it again with 45 degrees, the only number you'll have to change is the angle. So we'll do this same problem again with 45 degrees. And if we do that, we end up with 70.5. Okay. So it's even wider now. 70.5. Okay, let's do one more time with 48. So let's get rid of 45, plug in 48, see what we get. We get 82 degrees. What do you notice about this angle? What's about to happen to it? Well, if you notice, as our angle on the bottom gets bigger, our angle of incidence, 40 degrees, 45 degrees, 48 degrees. As that angle is getting bigger, so is the angle of refraction, 59 degrees, the 70.5 degrees, and our 82 degrees. It's getting bigger and bigger and bigger. What number is our angle of refraction? What is this number about to hit? Well, it's about to hit 90 degrees. How could it refract into air more than 90 degrees? It can't. It physically can't. So let's see what happens if we plug in 49. So we plug in 49 degrees into our calculator, and it turns out we get no solution. We get undefined. So it physically does not refract. So no refraction. So if it doesn't refract, what does it do? Well, it turns out it reflects. So we can draw it reflecting at that same 49 degree angle. Well, has it always been reflecting a little bit? It turns out it has. There's always been a little bit of this light that has been reflecting this whole time, and some that's been refracting. We've been ignoring the reflection for right now because we've been concentrating on the refraction, but it's been reflecting this whole time. So it turns out once you get past a certain angle, it does not refract anymore, and you get only reflections. This phenomenon right here, where you get no refraction, is called total internal reflection. Okay, total internal reflection. Okay, and it happens when the angle you're coming in at is too big. Okay, let's go to our next slide and see how we could figure out what exact angle in between 48 and 49 it makes that transition from refracting to not refracting. Okay, So here we've redrawn this, and we have the light coming in at some angle. We're going to call this angle the critical angle. Okay? So at the critical angle, it's not going to refract a lot out here. It's not going to do total internal reflection. It is going to strictly, make my pen a little bit thicker here, go at 90 degrees. So here it is at this angle right here is 90 degrees. So it is just on the edge of refracting or not. If the critical angle were any smaller, then it would just give you a normal ray out here. And if it were any bigger, it wouldn't do this at all, and it would just reflect. So we're somewhere in between those two, right at this exact point called the critical angle. So let's plug in these numbers and see if we can solve, in general, for this number right here, the critical angle. So N1 and N2 we'll plug in. Our theta 1 in this case is the critical angle. N2. And our theta 2 is going to be 90 degrees. Let me unbold my pen real quick. Okay. What is the sine of 90 degrees? It turns out the sine of 90 degrees is 1. Exactly 1. Okay? So now let's solve for the sine. Let's continue to solve for the critical angle over here. Okay, so we'll divide by N1. So we get sine of the critical angle is equal to N2 over N1. And now again, we're going to have to take the arc sine of both sides. So we get that the critical angle is equal to the arc sine of N2 over N1. Okay, so this is our formula right here for the critical angle. Now what's important about N2 and N1? Well, N1 needs to be a large N compared to N2, which needs to be a small n. Because if you have n times the sine of your angle, okay, if your index of refraction goes down, like it did here from a large n to a small n, then your angle is going to have to go up. But your angle can only go up so much, eventually it's going to hit 90 degrees and it will not refract anymore. So your N1 has to be greater than N2 for this to work. If you try and do it the other way, it literally won't work in your calculator. It's mathematically undefined, and that's what will come back as in your calculator. So if you type in solving for a critical angle in your calculator by doing the arc sine, and you get undefined, that means one of two things. One is that there is no critical angle for that particular setup because your N2 is greater than N1. Or you've flipped N1 and N2 and you need to flip them back and do them the other way around. Alright, that is a critical angle.